Hello class. So we abruptly finished the last module. Sorry for that, but I got distracted with something else, so I just cut it off there. But here we're going to focus on atomic spectra now. So we are going to relate that to the Bohr model. A lot of us have seen the Bohr model before, but now we're going to go ahead and explain the emission spectrum with the Bohr model. Now, we talked about line spectra in the last module, but here, let me just write that again. The line spectra is also called an emission spectrum. These are when you have colored lines on a black background. Now, there's also absorption spectrum, so I'm trying to show that to you guys in case you see them online. We aren't going to focus on those. We are focusing primarily on emission spectra. So let's talk about Bohr. So Bohr, he used quantum mechanical principles to describe an atom. And he stated that the electron will orbit the nucleus. And he also stated that electrons have fixed orbits where the energy is constant. Okay, so electrons have fixed orbits where energy is constant for the electron. And electrons can change orbits with a loss or gain of a fixed discrete energy. So the hydrogen atom has only certain energy levels then, and he said that these are stationary states. Now these energy levels, or the orbits, we denote with an N. Okay, so N corresponds with our orbit number. And so we can have n equals 1, n equals 2, etc. And I'll show you a picture on the next page. Okay, so that's not an H, that's an N. I'm making it look more terrible. Here, I'm just going to write the N. Okay, and let's go over a few other things for the Bohr model. The space between the orbits is forbidden. So you will not find an electron in between orbits. And when our electrons change orbits, the electron jumps from one orbit to another without spending time in between orbits. Okay, and energy is needed for an electron to jump up an energy level. And when an electron drops an energy level, energy is given off. And it's given off or released in the form of light. And sometimes this light is visible light. Okay, so now I want to show you what his model looks like. So here's his model. Notice the n's, n equals 1, 2, 3, 4, and 5. N equals 1, 2, 3, 4, and 5. So the higher the energy level, the farther the orbit is from the nucleus. And here, what I want to point out here is the line spectra for hydrogen again. So this is the line spectra for hydrogen. So here I want to point out red first. So let's go over red. So again, here we have our orbits, and we see that the electron is going from 3 to 2. So initially, it was in the nucleus. I'm sorry. So initially, so we have n equals 1 here, close to the nucleus. And then ours is coming down from n equals 3 to n equals 2. So the electron got excited, and then it relaxed back down. And when it does that, it's going to emit a photon, or the packet of light. So if you guys recall, the formula for that before was the energy was equal to h times nu. So here again, this represents our photon of light. Now, to contrast this, let's talk about violet. So now here, violet goes from 5 to 2. So I'm just going to keep it n equals 2. So remember again, the Balmer series focused on visible light. So it's going to fall back to energy level 2 or orbit 2. And I'm going to make this larger here, bigger distance. So it's further away. There's your n equals 5. So it was excited up. Needed energy to do that. And then here it's going to relax back down. And it's going to also emit a photon of light. So there's our photon. And here, why we see red versus violet, notice that the transition here between 3 and 2 is you need less energy to excite and relax from the 2 to 3 or 3 to 2 orbits than you do from the 5 to 2. And that should make sense when we learned about energy. Now, which has a higher energy, violet or red? Well, violet light is more energetic. It has higher energy than red. And that should make sense. The amount of energy it takes to excite has to equal the amount of energy it takes to emit. So here, it goes through more orbits, so it goes through more energy levels, so it's going to have a higher energy light. Okay. So here, let's write this. So our E, energy, equals our Planck's constant times nu. This is our energy of our photon, and it equals the difference between two energy states. Okay. All right. So let's go ahead and look at an example. So we have a hydrogen atom. It absorbs a photon of UV light, and its electron enters the n equals 4 energy level. Calculate the change in energy of the atom and the wavelength in nanometers of the photon. Now, we're going to go back to a formula that we saw before in a previous module, but we know that our change in E, because it wants to change in energy, right? So we have to use the proper Rydberg formula. So change in E equals 2.18 times 10 to the negative 18 joules times, and we know that it was 1 over our n1 squared minus 1 over our n2 squared times our z squared. So this was our Rydberg, but we care about energy. So what should the energy be? We should hope to get joules out. And so with this formula now, let's just go ahead and plug everything in. So our delta E equals 2.18 times 10 to the negative 18 joules times. Now here, it enters the n equals 4. Well, where is it starting from? Well, it must start from n equals 1, right? The orbit closest to the nucleus. So 1 over 1 squared minus, and where did it go? It enters the n equals 4. So 1 over 4 squared. And this is hydrogen atom. So if you guys recall Z, that's going to be the what for hydrogen. I guess I'm acting like you guys are in class, but this tells us that we have a Z of 1. So here our Z has to be 1 squared. And then when we solve, you should get 2.04 times 10 to the negative 18 joules. Now, because it's positive, It's a positive change in energy. We know that this must have been the energy that's absorbed to go from n equals 1 to n equals 4. Okay, hopefully that makes sense. Now part B asks what is the wavelength in nanometers of the photon. So if we look at part B, our formula is going to be E equals Planck's constant times the speed of light, all divided by our wavelength. So we know we want to solve for our wavelength. We have our energy now from the previous example, so we're just going to rearrange. So our lambda equals hc over our energy. Let's just plug it in. So 6.626 times 10 to the negative 34. So that's Planck's constant. We've talked about that quite a bit. And we know the speed of light is 3 times 10 to the 8 meters per second. And our energy we just calculated. That's 2.04 times 10 to the negative 18 joules. So here we'll cancel joules, we'll cancel seconds, and we're left with meters. But the question asks for it in nanometers, so that's going to equal 9.74 times 10 to the negative 8 meters. So now we just convert to nanometers. So we know that in a meter, there's 10 to the 9 nanometers. So in the end, we're going to have 97.4 nanometers. Okay. So these are typical examples that you're going to see. I'll put more in the discussion and our homework. Now, the last thing I need to say about the Bohr model is it has limitations. So it's really only used for the hydrogen atom, and so it can't explain emission spectra of atoms or ions with more than one electron. And we know that electrons don't travel in fixed orbits. And this actually now, you're going to see in the next modules, we're going to shift to newer ideas leading to the newer quantum mechanics. Okay, so we're going to study something called the wave-particle duality, which is de Broglie's equation, and the uncertainty principle. Okay, on to the next module.